theoretically, it should be recording me right now, and things should be on their way. So if you haven't done so already, just pull up this file from Google. It's 01 static electricity. It's under the PowerPoint section. Right. As we go on this, I'm going to make some annotations on it, and I'll post that here specifically later. Okay. If you have a hard time understanding what I mean, just ask me. I don't mind explaining it over. So the first topic is static electricity. And anyone here live in NDG? Or near NDG, Westman area? Which part of it? Metro West? NDG, which part of NDG? Sherbrooke Cavendish? Okay. Anyone live a little bit more east than that on Sherbrooke, near the Carey? Have you guys listened to the news about what happened yesterday? Yeah, did you see the pictures of the park? Yeah. It's crazy. Like, okay, so the story is that there's a park on the corner of a street called Gr.00003 and Sherbrooke, and which is actually really close to where I live. And because of the storm yesterday, a lot of the trees were broken, and the park looks like it was flattened. There's like trees all over the ground. It's crazy how much wind there was yesterday. If you keep going on Sherbrooke eastward, there's a street called Gr.00003. Yeah, okay. So there's like a gas station there, and on Gr.00003 there's a tree that was struck by lightning, and the tree fell. Like big, I'm talking about an old tree like this thick, was struck by lightning and totally split in half. It crashed on the house across the street. It was pretty cool to watch, really scary, of course, for anyone who got to live through that. But it goes to show you the power of that lightning and how messed up it was. I'm mentioning all this because that's an example of static electricity. Anyone know other examples of static electricity? Yeah? Balloons. Balloons? Yeah, that's what I have in there. What about balloons? Can you be more specific?
Well, I mean, like if, for example, you rub a balloon against your skin, but it would be like static electricity.
Yeah, it'll create static electricity. Okay. Yeah, exactly. Have you ever seen that episode of Family Guy where Peter's walking around the ride and shocking things? Yeah, absolutely. Anything else? Static electricity, right? Anyone ever touch a doorknob and like stab? Yeah, that's static electricity. Using a camera flash. That's a type of static electricity. They're used in circuits, but it's a principle of static electricity that causes the flash event. Especially the older cameras. The cameras now are a little bit more digital, but the old cameras with big flash balls, that's static electricity. Those are examples of static electricity. Yeah.
There's still like full screen balls that touch and you hear it.
Yeah, absolutely. You know what that's called?
No, I don't know.
Anyone know what those things are called? You put your hand on it and your hair goes up?
Is it the like Tesla?
No, I think there's something similar that might be called that, but that's not what this one is called. But I know what you're talking about. It looks similar. It's called a name, guys. It's called the Van de Graaff machine. Yeah. No, okay, I didn't expect anyone to know that. It's called a Van de Graaff machine or a Van de Graaff generator. I'm going to write that up more later. And yeah, that produces static electricity. I actually have a recommended staple. We're talking about static electricity. What other types of electricity is there? Or what does static mean? By the way, I do this thing where I awkwardly don't say anything until I answer. Until one of you guys answer. Okay. Part of static is non-movement. Okay, so if that's one type of electricity, what's another type of electricity? Kinetic. We don't use that term, but you're right. What do you mean by that? Whenever there's movement. Okay, so what has, now we're going to get to it, what has a movement of electricity? Hydroelectricity? Yes. Be a little bit more specific. I'm looking for something more specific. You're right. You're right. Yeah?
Direct circuits and alternators.
Circuits. Circuits is a movement of electrons, a movement of electricity, right? That's the opposite of static electricity, right? Circuits. So we're going to be learning about both of those. We're starting with static, which is the non of electricity. So I have some learning objectives here for you. Basically, what it comes down to is you understanding how these things apply. So one thing that's super, super important in this course is that you understand why you're learning what you're learning. All right? Who has done good in Cal 2, for example, and you learn how to do integrals, and you're given this machine, which is like integrates this. Integrate it. And then you're like, yeah, absolutely. Use the substitution rule, use the trig identity, da 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 da. You get an answer. I have no idea. Is this even a possible integral? Is this an identity? You guys know this one off by heart? I have no idea. Anyways, the point is you just did something, but you don't know why you did it. Your Cal teachers are amazing, and they're going to tell you why this is useful, or at least I hope they did. And it's really important. I just realized that looks weird. Variables. Okay. The purpose of you guys being here is not just to learn how to integrate that, it's to learn how to apply that later on. Right? It's super important. What is the purpose of integration? You guys know? Inverse derivative. What's the derivative? Yeah. What? That derivative is to determine the slope or the instantaneous slope at a given time with a rate of change or something. So what would integrals be? Area under the curve? Is that what you're going to say? What does that mean, area under the curve? Why do you need to find the area underneath the curve? And why is that important? It's not my life. I have not once had to find the area underneath the curve. I've had to do integrals, but never an area underneath the curve. The certain energy or something? You could use it to, I want a more mathematical answer, not a physics answer. Why would integrals be important? So integrals, the symbol at the beginning means what? What does the symbol mean? Sum, actually, exactly it. So if you want to add a bunch of things mathematically, it's a lot faster to add if you do this process called integration. All right, so for example, if you want to determine what the area of a circle is, for example, because we're going to be using that in this class, you take, let's say, this point has a radius r, right? And you add up all these other points around the circle, and then you end up getting something called 2 pi r or whatever. Right? The way you got that is by adding up all these really small things. That's what integrals are. It's adding up a bunch of small things. You guys know that small d means small, and the thing that you're adding up is whatever's in front of the d. So it has a purpose, and everything we're doing here has a purpose. You guys want to learn about circuits and calculating resistances and all that stuff? It doesn't mean nothing unless you know why you're learning it. Okay? So it says here, analyze situations in physics associated with static electricity. I want you guys to know why you're learning. If at any point you feel like, I have no idea why I'm learning this, tell me, and then I'll try to make it a bit more obvious. Okay? Maybe? Okay. So let's get started. So we learned about this already. There is a huge history about this. I'm not going to go into detail because we're actually going to learn all of what all these guys discovered as the course progresses. Just needs you to know that this thing is, electricity is quite old. It's not something that's newly discovered. And we just found better ways to exploit it recently. And it's pretty cool. Once we get to Kirchhoff's law and something called the Hall effect, I think you guys will find it quite interesting. So what is static electricity? We talked about it. If you haven't written this down, it's basically it's a buildup of charge, okay? So when we're talking about something getting shocked, you're getting shocked by a charge that was building up there for a while, all right? In a lightning storm, where is the charge building up? In the cloud, exactly. called static because the charges don't move. We talked about that. Also, if I'm going fast, tell me to slow down. If I'm going slow, tell me to speed up. Okay? You don't have to say it in front of everyone because you don't want to look like a jackass. Just, you can tell me whenever. Good? So what you guys have in front of you, the computers, all that stuff, it's the opposite of static electricity. Those are circuits. They're moving electricity. So we're not going to categorize those just yet. We're not going to talk about those just yet. Anyone in this class left-handed? Just Marco? Oh, and okay. Let me try to remember your name. Don't tell me. Michelle? We're good? Any questions? All right, so now we're talking about what a charge is, because I said static electricity is a buildup of a charge. What physical thing, matter, am I talking about when I'm talking about charge? Awkward. I'm going to wait. Electrons. Yeah. Did you say that? Okay. Electrons, and it doesn't have to be electrons. It could also be protons. Yeah. Say it louder. This room has this weird echo, or I can't hear well. Do you guys hear me at the back? Marco, can you hear me? Yeah? In the back there, you can hear me? What's your name? Amanda? Okay. If you can't hear me, let me know. It's important that you do hear me. Exactly. So it's a measure of electrons and protons. And we can count electrons and protons, but it's not efficient because there's just so many electrons and protons that it's not worth it to measure it in the number of charges, but in the value of that charge. And we came up with like Avogadro's number. You guys know what Avogadro's number is? Like, it's not a real thing, really. I mean, it's just the number of hydrogen atoms in 1 gram. Doesn't mean much, but it really is just an easier way of counting atoms. Atoms are just so plural, there's so many of them, that we just came up with this mole. Okay, whatever, it's many, it's like a dozen atoms or whatever. So the same thing here. So we call that a coulomb. And 1 coulomb is the equivalent of 6.2 times 10 to the 18 charges. Okay? That. And of course, 1 electron has to have a charge, just like 1 atom has to have a number of moles. How many moles are there in 1 atom? You guys know that number? Yeah. 1 over that number, right? Because it's that many atoms in 1 mole, so 1 divided by that number is how many moles there are in 1 atom. Okay? So it's the same thing here. If 1 coulomb is 6.2 times 10 to the 18 charges, 1 charge is 1 divided by that number. So if you do 1 over 1.6 times 10 to the negative 19 coulombs, you get 1 charge. So not one, yeah, you get not 1 charge. 1 coulomb. 1 coulomb. And this is not. This is charges. Okay? Okay with that? And that's the same thing as saying 6.2 times 10 to the 18 charges. Okay, I thought I fixed that. Okay, anyways. So we have these protons and electrons, and they each have a sign in front of them. Sorry, I'm blocking. They each have a sign in front of them. What does the plus and the minus mean? It's convention. Okay, it doesn't really mean much. Is it a vector? Is it a charge of vector? What does a vector mean? It's a scalar quantity, but it's got a positive and a negative in front of it, which could look like a vector, but it's not really a vector. It actually is a scalar quantity. What does a vector need to have in order to be considered a vector? Direction, yeah, absolutely. And a magnitude, yeah. This here is what we call the elementary charge. Okay? And an elementary charge is just the coulombic value of one electron or one proton. All right? I won't ask you to memorize this, but we'll use it so much that you'll have memorized it. Promise. Okay? I will have failed you if we did this whole course and you never used this. I would have not done my job as a teacher. We're good? Any questions? It's pretty straightforward so far. I gotta ask you guys a question just to get this into practice. By the way, what's that symbol here? Micro, which is the what? What is it? 10 to the negative 6. All right. So here we have a charge that's 10 to the negative 6 coulombs. Whoopsie. 10 to the negative 6 coulombs. All right. Come on. And I'm asking you, how many charges are there in this many coulombs? All right. So how could you solve this problem? Take 2 minutes. Try to solve it on your own, then we'll solve it together. It shouldn't be too difficult. Think of it as a unit conversion. You using yesterday's notes? Yeah, you have an answer? Let me know. 500 million? Billion? You might have there might be a more precise answer. How did you do that calculation?
I just did the 1.6 times. I did not. That charge divided by.
Okay, your math is right. It's funny that it gives you such a round answer. Okay, you did the right calculation. Yeah. 8 divided by 1.6 is 50? No, 5? 5? Okay. All right, so if I were to solve this, I would say that I want to figure out how many charges this is equal to. Right? But I know that, is it 1.6? No, I got my numbers wrong. I know that 1 coulomb is equal to how many charges? Eh? Yeah. So at this point, this is kind of just like a proportion. You can cross multiply, so this times this divided by this times this kind of thing. All right, and then we get that x is equal to, so Marco, you want to give me your answer? Times 10 to that. Are you sure it's 500 billion? Well, it seems a bit off. But it should give you the same answer though, right?
It's there's 11 zeros.
11 zeros? Someone got a different answer? What did you get? 4.9 times 10 to the 13? That sounds more reasonable to me. Because you have to add when you're multiplying this and this, you should add the exponents. So billion is, I don't know if that's correct. Okay. Billion would be times 10 to the 9, and this is times 10 to the 13. Anyway, close enough, it doesn't matter. What are the units? Protons, charges? I would accept both. Why do we know it's protons and not electrons? It's positive, exactly. Simple as that. Any questions? Yep.
Would it work if you could divide it by the charge?
That would work. If you did 8 times 10 to the 6 divided by 1.6 times 10 to the 19, you should get the same answer. Did you get it, the same answer? Try it out. If it's not, tell me, okay? All right, let's complete a couple sentences. Most objects do not contain charges. What are they referred to as when they don't contain a charge? Neutral. You're looking at yesterday's notes. All right. Yeah, it's neutral. All right. Okay, I don't know how to spell today. Neutral. Okay. And what does it mean when you're neutral? What's that? Absolutely. Okay. If anyone didn't hear that, it's that there are the same number of protons and electrons. So this means that the number of protons is equal to the number of electrons. What is another way of saying this statement? That the number of protons is equal to the number of electrons. By the way, what's the symbol for charge, or the variable? You know how in mechanics you had acceleration was A, velocity was V. What's the variable for charge? You guys remember that from grade 10, from secondaire 4? It's a long time ago now. Q, you guys remember that? No? So what could you tell me about the sum or the net charge in an object or in a something that's neutral? What's that? 0, absolutely. So you can say those two things mean the same thing. But the sum of the charge, or Q net, I shouldn't write the sum of Q net, but the Q net, or the sum of the charge, should be equal to 0. And that's how we know something is neutral. All right? It doesn't mean they have no charge. It means that they have an equal and opposite amount of charges. This is easy. If you have a deficit of electrons, you're considered to be, say that? Positively charged. This is kind of intuitive, right? If you have extra electrons, you are negative. Let me just do something real quick while you guys are doing that. Wow, how do I end the PowerPoint? I'll just go to the end. Okay. What can you say about two oppositely charged particles? This is something, again, it's more of a logic thing that you might have learned when you were younger or in other courses. Now we're going to learn it for the first time formally. So what can you say about two charges that are oppositely charged? Yeah. They attract, absolutely. All right. Don't write that yet? Yeah, right. Let's write that. We'll add a little bit to it. They attract. What does that mean, they attract? Because attract is not really a physics word. What's more of a physics word when it comes to things like that? So if I had two charged particles, what's going to happen to them? Right now, they're not moving. and I put them next to each other, what's going to happen to those two charged particles? What do you think?
They're going to get kinetic energy.
They're going to get kinetic energy. In order for there to gain energy, so what is kinetic energy? It's a
formula.
Yeah, tell me the formula for it.
It's E equal half the mass times the speed square.
Okay, so if it doesn't have a velocity, it doesn't have a kinetic energy, right? When I put them there, did they have a velocity? Not yet. But then they gained velocity. So what does that mean? If they gain velocity, that means they have acceleration. If they have acceleration, it means there is a... You're so close. Force, exactly. All right, so there's a force that's attracting these two particles together. All right, what is that force called?
Magnetic force.
Magnetic force? Is this a magnet? An electric force? Close. Closer than magnetic force, which is another force that we're going to learn about. And that's the most common answer that I get is magnetic force. It's called electrostatic force. Okay, let's write that up. They attract because of electrostatic force. And we're going to call that Fe. Not Fe as in the element iron, but F sub E for the force of electrostatic force. Forces are vectors? Yes or no? Yes. So we need to give it a vector symbol. And this whole principle is called Coulomb's law. And our next class is going to be, maybe even this class, because I think you guys are a bit faster than yesterday's class. Coulomb's law. We'll see. So Coulomb's law describes this force. We'll talk about it later. Okay? Are we good with that? Before I talk about that, just pull out the real obvious here. If I had two oppositely charged particles, what would happen? Sorry, two similarly charged particles, what would happen? Michelle? They would push off of each other. Is there still a force? Yes, just the force is in another direction. Okay? And it's called repulsion in that case. So attraction and repulsion. All right, so here's some more facts about static electricity. It's the imbalance of positive and negative charges. All right, so it can't be done in neutral objects. The objects have to be charged. The balloons, for example, sticking to a wall. They're the hair, when you're brushing your hair, when you're having a bad hair day. We'll talk about some of these. When you touch the door handle. All right. I'm going to get back to this in 1 second. Okay, you guys don't have this slide because I only added it at the last minute, but when you get it after with my annotations, you'll have it. I want to do a little demo. I need someone with hair because obviously I'm not the person to do this. These are dirty now, I guess. I'll pick out a new one. Can I have a volunteer that has long hair? Someone who doesn't mind messing it up. So we're talking about charges. Okay? Everyone needs to come here so everyone can shoot it. We're all talking about charges, and it's important to pay attention to that. So we know that oppositely charged things repel, and oppositely charged things attract, similarly charged things repel. What about neutral and neutral? What happens to that? Nothing, exactly. There's no attraction whatsoever. Is there an attraction between the balloon and, I'm trying to remember your name.
Close.
Okay. Is that out?
Yeah.
I did not know that. But thank you for this. Okay. All right. So right now there is no charge between the hair and the balloon. Okay, So what is the charge of these two things? Neutral, or at least one of them has to at least be neutral. Okay, we don't know both of them are neutral, but for sure one of them is neutral. Okay, so far so good? All right. All right, so what's going on here? So is there an attraction there? Yes, okay. What, the attraction is between what and what? What's that? The balloon and the hair. If you don't see that right now, your hair is stuck to the balloon. You can see that kind of? All right. What about, is there any repulsion happening? No repulsion happening? Okay, maybe there is, maybe there isn't. Let's try to figure that out. So does that mean these two objects are charged? The two objects being hair and balloon? Yes, if there is, and we're talking about static electricity, so I'm not going to trick you into, there's a magnetic force. No, there is an electrostatic force that's attracting the hair to the balloon. That means the hair and the balloon must be what in terms of their signs of their charges? Are they similar or opposite? Opposite, because there's an attraction. All right. So which one has which charge? I'll actually come back later. The hair is messing up. So in order to understand which one's negative and which one's positive, there is a property in the carbon and, first of all, what is hair made of, by the way? Which is what? What type of molecule is it? It's a protein. If it's a protein, what atoms are there in proteins? Organic ones, which are which ones?
CHNO. Sometimes phosphorus.
Yeah, and you got them all except for one.
I know.
Just
hydrogen. No, I said, I don't know.
Sulfur. You're gonna say that? Sulfur. Okay, yeah. So those atoms are in these hair, right? And there's some, probably mostly carbon because it's rubber. A lot of carbon atoms in this as well. And so the composition of those atoms, let's swing that around. The composition of those atoms will make it so that one prefers to get the electrons, one prefers to lose their electrons. Kind of like acids and bases, but don't think of them like acids and bases because they're not acids and bases. But one of them is most likely to receive electrons, the other one is most likely to give their electrons, and that's where this comes in. All right. So the two things that we're comparing is hair and balloon. All right. And the higher you are on this list, the more likely you are to be positive. Okay. After friction. So the hair in this case, I would say, is positive, and the balloon is negative. What happened? Tell me. Did the electrons go from this hair to the balloon, or do the protons go from the balloon to the hair, or is it both? Electrons from the hair to the balloon. Okay. Anyone else have an idea? Say that again. Always travels from negative to positive. I guess you're right. It is always that. But why? Why? Yes, they're heavy compared to electrons. That's not necessarily the reason. Why is it that it's the electrons moving and not the protons? Yeah. Okay, so that's part of it. You're getting there. What is the middle of the atom called? The nucleus or the noyau or whatever you there. And what does that determine? What does the noyau determine?
The mass.
The mass and also the charge. Yes and no, because you don't know how many electrons there are. I'm just talking about the noyau. The nature of the atom, which means what? Just which atom it is. Yeah. Exactly. So which atom it is determined by neutrons. Is it determined by neutrons? Because then you have isotopes, which are not, so it's not neutrons. It's determined by protons, exactly. And if you had things that are protons leaving Melanie's hair, that doesn't make any sense, because that would mean that the composition of her hair would be changing. It would be going from being a protein to being like oxygen or something with less protons or something like that. You know? which doesn't make any sense at all. The matter is not changing. The charge of the matter is changing, so therefore it has to be electrons that are flowing. So where do the electrons go? Well, in this case, we look at the chart. This is called the triboelectric series. I don't expect you to memorize this. Don't worry. If I ask you a question, I'll give you a chart. So you use this chart to determine what's going to become negative and what's going to become positive. So in this case, I rub the balloon onto Melanie's hair, and the balloon becomes negative, and the hair becomes positive. So now the hair is positive, the balloon's negative. What is going to happen between those two? They're attracting, okay? And Melanie's hair is wet. What's the charge?
Positive.
Positive. So if it's positive, one piece of hair is positive. What's the next piece of hair? Is the next piece of hair next to it also positive, or is that a negative? It's also positive.
So they have repulsion.
So there is repulsion, right? Right? So the hairs will repel each other as well. Right? So that's why her hair wasn't going up in one big strand. It was frizzling. It was all trying to get away from each other, all coming towards the balloon. Okay? Take 2 minutes to write that down in this slide. Okay? Talk about, if you're not sure of the explanation, ask me or ask the person next to you. Try to write it in your own words. Okay, I'll write it too. But try to write it in your own words. Okay? Someone want to read me their answer? I'm going to wait awkwardly until you volunteer, otherwise I'll just point to someone. I just want to hear what you might have written. Mark.
I said friction creates electrostatic force. Air positive, balloon negative. Negative balloon attracts the air, and therefore, the air repels the other air because they are both positive.
Okay. One thing I would change, though, you said that friction causes electrostatic force. That's not necessarily true. What friction is doing is causing the electrons to move from one to the other, and the difference in charge is what's creating the force. Okay, maybe you want to change it. Very good. Thank you so much for volunteering that. Anyone else want to read me theirs? Or are we done with that? I'd love to hear your answers. It's just I know you're shy about it. Okay, we'll move on. There's 2 more demos that I'm going to ask you guys to explain. And Mark has done more than his share now. All right, next one is water and rock. Okay, we're going to use the Van de Graaff generator now. Just had that line around you. keep electronics away from these machines because they'll produce an enormous amount of static electricity. All right. So what this thing does, by the way, this is a conducting surface and this is a conducting surface. All right. They're both, if you go back to the triboelectric series, they're both the same material here. So neither one nor the other is higher. All right. It's the exact same material, theoretically. And this thing, can you guys see in here, there's like a belt that's going to go up and down like this. That belt is going to create friction and cause static electricity to form. We good with that so far? So we'll turn that on. All right? And what this does is it creates a positive, it's humid today. What this does is create a positive charge around the surface of this thing. Okay? So the negative charges are being grounded and sent into here in the ground. All right? So electrons are escaping. This is becoming positive. Right now, this is neutral now because it's off. This is neutral because I'm touching it. There's no charge. Even if there was a charge, I'm grounding it. So the electrons are going to me or my electrons are going to it. And so it's neutral, no forces or nothing like that. So far, so good? Now I'm creating positive charge. I won't turn it on so high. But now there's a positive charge on this thing, on the surface of this thing. What's the charge of this? Neutral. If I bring it close, what's happening? Something's happening. You don't know it, but something's happening. What's that? You're saying right things. Can you just say louder?
All right. Since this is getting, the big orb is getting positive, right?
Yeah.
So the electrons from your small orb are going to your big orb.
Very good observation. Not super correct, but the right idea. All right. So he's saying, Marco is saying that the electrons are getting closer to that. Are they jumping across? If I was close enough and it was humid enough, it would jump across. That's what lightning is. That's what the shock is. But there is no shock. There is no lightning. So are my electrons jumping across? Say that again. They want to, but they can't. So what's happening in this thing? Yes. It's creating a negative charge on this side. All the electrons are moving on this side. All right. What's happening to this side? Are the positives moving that way? No, because the protons don't move. But if there is less electrons, if there's less electrons, it means that it's positive. Not even just partially, but it's positive. So this part's going to be negative. This part's going to be positive. If I move it away, does it go back to being normal? Because there was electrons here and protons here. So the protons are going to attract the electrons back. Let's say I turn this off. Let's say I turn this off. So now it's back to being neutral. Correct? Okay. Now I'm touching it. What's happening? So remember, this thing is positive, and that thing, the electrons were moving towards the positive. Before it couldn't get there because it wasn't touching. Now it's touching. Now what's happening? Say that again?
They're both becoming positive.
What's both? What two things are you talking about? This and that? Yeah. Both things are becoming positive?
Yeah.
Más o menos. Plus ou moins. What do you mean? Do you want to explain that?
Well, I mean, like, if they can now transfer in the big orb, and the big orb takes all like the electrons away, therefore.
Okay, so the orb takes the electrons away. So now are those electrons in here now?
Well,
say that? They're getting drained into this. So the electrons from this are leaving and going into the big ball. So if I remove this now, what's the charge of this? Positive, because all the electrons went there and left behind the positive charges. Right? All right? And let's restart. All right? Let's say we do the same thing. We restarted. Everything was neutral before. Now we're doing this. The electrons are here. And now I turned it off. I turned it off, and then I went back. What's the charge now? Yeah, neutral. Why? Exactly. This thing was positive. That thing was now neutral because it got its theoretic charges from here. And the electrons flow back. So now this is actually uncharged as neutral. So in order for me to charge this, I have to take it away before turning it off. Okay, let's go back. So it's on. Wait a little bit. All right, waiting a little bit so the electrons go in here. This is becoming positively charged. Now this is positively charged, right? And now I'm turning this off. This is still positively charged. Now the experiment is, and yesterday it did not work because life sucks. But here we go. Oh, here we go. It works perfect. You see that? It's attracting the water. What charge is this?
Positive.
Positive. What charge is the water? I just touched the water briefly, and now it's no longer attracted because it got grounded. The water is negatively charged water. That sounds pretty dangerous to me. Water is neutral. What's the term that we use for water when it comes to like electric charges? You might have learned this in organic class a little bit. Have you guys taken organic? Maybe it's in chemistry class. Exactly, it's polar. What does polar mean? Okay, exactly. So can someone describe to me what water looks like, the molecule?
It's like pH.
Okay, triangle like that. Yeah, and what's in the middle? Oxygen. What's on the side? Which one of those is negatively charged? Not charged, but partially negative. Oxygen is more electronegative because it's rightmost on the periodic table. Hydrogen is the leftmost on the periodic table, so it's going to be the most positive, right? So this thing was what charge?
Positive.
So what was it attracting?
The oxygen.
Exactly. It's attracting the oxygen part of water molecules, and it's causing it to bend towards it, right? We said this is positively charged, right? Not done yet. Then I think I have that. What's the charge of balloon going to be after a negative? It's going to be negative. So does that mean what is it going to do with the water? Is it going to repel the water or attract the water? Repel? Anyone else have an idea? Is it going to do nothing to the water? Is it repel or attract? Those are three only answers. Think about it. I'm going to give you 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It's attracting it.
It's attracting.
Now it's attracting the hydrogen atom, because remember, water is polar. Actually, when I taught this class yesterday, I had no idea why it was that. And I was like, I thought the balloon becomes negative, and then the students were telling me maybe it becomes positive. Maybe I'm reading that chart wrong. But it turns out, you guys know how to make? Or how about? He's the one who came up and we find the atoms together. And it's because the water molecules are polar that they're being attracted in both situations.
That maybe kind of get attracted and repulsed at the same time.
The reason why the molecule is that angle is because it's being repulsed and attracted at the same time. Alright, you guys know what pi orbitals are? Pi orbitals? Again, you'll learn it in organic class, but there is pi orbitals, pi electrons there that are causing it for it to be this angle, which is different from carbon dioxide, which is at 180 degree angle. And here, it's not at 180 degree angle. Okay? That's because of these pi orbitals here. Okay? But yeah, so there's some internal repulsion and attraction happening. So these two are repelling each other, and it's being, they're trying to be as far as they can from each other, but they can't because there's no room from these electrons repulsing each other. Complicated quantum mechanics stuff, don't worry too much about it. Okay, so let's write that one down too. Alright, so in the demo 2 slide, write down what you saw happen with the Van de Graaff, with the touching, with the bringing close, all that stuff. I'll give you a bit more time for this one because there's a lot of things that happened. I'm sorry? Oh, yes, absolutely. It's called a Van der Graaf machine. Van der Graaf. Oops. Graaf generator. Class ends at 10:30. Oh, very good. So while you're writing, I'll write mine, but I'm still going to ask you for you to read me yours. Yeah. Someone want to read me their answer? Please. It's funny. Yeah, you want to go, Michael? The whole person. Well, whatever you want.
Basically, a row that electron will move along the same object towards something positive. Positive the other side could be some positive as well, but will not transfer unless proper conductor is between both objects.
Okay.
Also, if the positively charged object is now suddenly neutral, all electrons that were previously transferred to the other object will return to the original. Also wrote that water, being a polar molecule, is both positive and negative, so it will be attracted to both positively or negatively charged.
Okay. Very good. Very good. Anyone else? There's another demo, so I'll be asking someone else. I did the mark. It's funny, the other class is mostly guys, this one's mostly girls.
It's about the science mostly.
Oh, you guys are mostly outside? But I thought it was mixed. Yesterday's class was mixed. It was like almost half and half. So all the girls are in pure and all the guys are. I used to teach at, I told you guys, I taught at all girls school, and it was weird. When we used to send them off to their CJEP application, there was like 90% of my students went into health science, and maybe only 10% went into pure and applied. And the whole time I was there, I was trying to make it so that I was equal. Because have you guys heard of, it's not gender inequality, it's literally just the perception of the field of the pure and applied sciences, for some reason, is not attractive to women. And there shouldn't be that case at all, because women actually are better critical thinkers in that kind of job than guys are. And I can't imagine how much better the field would be if there was more women in those pure and applied subjects. It's nice. Keep that in mind. Okay, before I do my third demo, I actually want to ask you guys something special. Put my life at risk here. No, not really. It's not really all that dangerous. What's the charge? What's the charge of this? Overall neutral. This part is positive. And this part is, sorry, this part's negative, this part is positive. I'm going to touch this now. But these two things are not touching. I'm going to touch it. All right? What's the charge of that thing? Think about it. I'm going to do it again. So this thing, restart everything, all right? Everything is neutral. Turn this thing on. I'm not touching it. These two things are not touching. And I'm touching this. And I'm taking it away. What's the charge of this thing now? Who wants to try and give me an answer? Go ahead. It's what? Can you explain to me why? So the electrons were here, and the positive charges are here. So there are more positive charges here, rather. And I touched it, and what happens? But the electrons are being attracted to that. So why would they go to me? I'm more neutral? You're right, I am neutral, but I'm also made up of many electrons, and I'm made up of many protons. What do you think, Bronwyn? Your answer is right. Your explanation isn't. So it does become negatively charged. This is now negatively charged. Why? Where are those negative charges coming from?
Because all the electrons are in one place, the rest becomes a positively charged object. So when you touch it, it's trying to become neutral again. It's easier to take electrons from you than from the attractive electrons.
Absolutely. You guys understand that? All right. So I was giving my electrons to this, and this is now negative. Is that what you were saying before, Brahma? Maybe I misunderstood it. But that's where it's getting its negative charge. It's getting them from me, right? So it's the ground, and I'm not the ground, right? So the ground is where the electrons go. So I touched it. My electrons went there. I'm not technically charged, but I have so many charges that you can basically consider me as neutral still. Also, I'm touching the ground, which means that I get my electrons back right away. And so essentially this thing is getting its electrons from me, and it's becoming negatively charged. So if I were to do that, will it attract or repel Melanie's hair? Attract. So let's see if I'm right. Please let this work, because otherwise I will not have convinced you very well. All right, I do that. Melanie, you want to come? So I'm going to touch it. All right. I can feel it all the way down my arm. All right, come closer here. And of course, it doesn't work. There's maybe one strand, but it's not working super well. Okay, that's what's supposed to happen. Believe me. All right. Last demo is this thing here, and this is called an electroscope. All right. these two balls are hanging. They're styrofoam balls, but they're painted with a conductive paint. Okay, so they're silver color. They're painted with conductive paint. They're very light. And it's important for this. They're hanging by wires that are conductors as well. And they're attached to this metal bar here, which is conductive. And at the top of this metal bar that's conductive, there's a ball that's also conductive. Everything else is non-conductive. Okay? So I'm going to put that here. And here's what I'm going to do. I'm going to charge my rod the same way we did before. Alright. Maybe not as much. Tanya and I find out that the slower this thing works, the better it does for some reason. Alright. And now, what's the charge of this? Positive. And here's what I'm going to do. I'm going to bring it close to this thing. Tell me what's going to happen. It's going to stick to it. What's the charge of this? Is it negative? Right now it's neutral. Alright. So what's going to happen? What do you guys think is going to happen? I want guesses. I don't want right answers. I want guesses. Both balls will become positive, and then what's going to happen? If they both become positive, then they will repel. Explain why.
Because this has a very strong positive charge and has some neutrals. So put both together. Positive charge will finish, but I don't think it'll duplicate. It says this can't, it's not good. This is like ground.
Okay. So you can add a little bit more to that? Okay.
Since everything is neutral, the electrons from the two inside are going to go back to the top of the ball and then they're going to become positive.
Yeah, exactly. So the electrons are going to get attracted and come to as close as they possibly can to the top, right? If I'm not touching this, they're never going to transfer over. And then they're going to leave the positive charges behind, and positive repels positive. So those two balls should technically separate from each other. You guys want to just move closer so that you can see that? That a little bit. Let me try that again. And then I have a super question for you guys afterwards. Is what's going to happen if I touch that metal bar? Let's try it again. Yeah, a little bit. You guys see it? Okay. These things work less and less well when it's humid, and we've got like 2 of the most humid days of the summer so far. Okay, so we explained why that happens. What's going to happen, theoretically, because again, I have horrible luck with these things and they're not working very well for me. What's going to happen if I touch it? What should happen when I touch it? And then remove it. What do you think? Why? You're right, the answer's right.
Electrons will jump to the
Exactly. So it'll be more permanent. If I didn't touch it, this thing is still overall neutral. And when I remove it, the electrons just go back down and the balls are neutral and they collapse and they fall because of gravity. But if I touch it, the electrons actually leave it permanently, right? Leaving that whole thing to be positively charged. So it should stay separated for a long period of time. I bet you anything it's not going to work, but please believe me, that's what happens. All right? Touch, touch, touch. This is not positively charged. Right, we're going to touch this. Right, and they're repelling, and they're starting to die off. If you put that on forward, I think that's right. Do this. There you go. I thought it would be more obvious than that, but yeah, you can definitely see that they're being repelled from each other. Cool, eh? All right, write that down, please. once you're done writing it, take a 5-minute break. Let's meet back here at 10:05, or just before 10:05. I said 10:03. Okay? 10:05. 10:05. Come back at 10:05. Don't forget, a great way to take notes is also to make drawings. So if you need to draw something, draw it for yourself, draw where the positive and negative charges are. Things might make more sense for you that way. This?
Yeah.
It's a belt that moves, that goes in a circle like that, causing just friction, electricity.
So okay, so basically this is like the balloon.
Yeah, and the internal components would be the air.
Yeah.
The electrons are escaping through the ground and going into the outlet.
Oh, that's pretty cool.
Yeah.
So I thought it was more complicated.
No, it's super simple. Yeah.
Thanks.
No problem. How much break time do you guys have between classes? None? So as soon as this one's over, the next one starts?
Yeah.
That's on Wednesdays when we had at 12:30.
Okay. But on other days, how does it work?
Depends.
Yeah.
I pretty much make a schedule.
Okay, got it. So is there a class today at exactly 10:30?
I don't
Hey?
I don't know if it's here.
Oh, okay. I don't know. I was going to suggest if no one has class, then we can start class a little bit later, but we can't do that. Can I have one of your answers, please? Anyone? Not Mark and not Marco. Thank you guys. Someone's answer for this? Some explanation that you might have written down or drawing that you wrote down? Sure. Is there a writing that goes with it? Okay, so it's very good. How about it? Okay. So, no, this already. Good enough for me, thank you. All right, so here's what you guys are going to do for the next 23 minutes. Skip a couple slides until you see a slide with a YouTube link. I want you guys to go to that YouTube link. It's a bunch of static electricity kind of demos like this. I want you guys to attempt to explain them all using the logic that we created. Right? So you guys have an understanding about how static electricity works and how the coulombic or the electrostatic force works. I want you guys to use that, try to explain it, work in groups if you want, work alone if you prefer alone, but talking about it with someone else is the best way of doing this, okay? So I encourage you guys to get into small groups and try to discuss it, explain it to those who don't understand, don't be afraid to ask questions, to me, to your friends. That's how we learn, right? So that's what we're doing for the next, until the end of class. That might be unfortunately.